Good evening and welcome to this evening's webinar, Specialist Mathematics Unit 3, Complex Numbers, hosted by Texas Instruments Australia. My name is Rodney Anderson and I will be your host for the webinar. This webinar is being recorded, will be available to view at a later date via on-the-demand along with the other panelist documents. It is recommended that you view the webinar and not try the activities as you watch live, as you can pause, fast forward and rewind the recorded webinar at a later date. During the webinar, if you actually have any questions or would like to chat and direct them to me, personally the host, you can use your mouse and toggle up towards the middle of the top of your screen and down or drop a toolbar. Look for the chat icon and type in your questions there. And through the webinar, as I said before, can you direct them to me, the host, and I'll ask the presenters to answer some of the questions of all the questions we can during the webinar. At the end of the webinar tonight, please take the time to complete the survey that comes up on the screen. It gives feedback to Texas Instruments Australia and the presenters how to improve on the high quality product that is produced, and we'll use that feedback to improve on webinars in future series. At the conclusion of the webinar, you will get an email within possibly 48 hours, and also you'll be given links to download and print off your participation certificate for your professional development. Now, our presenter tonight is Peter Flynn, who's the lecturer at the University of Melbourne. As you're well aware, he's a very experienced presenter, and he, as you see in the last sentence, he generously shares his experience mentoring and presenting at conferences locally and internationally. And our first presenter for the night is Raymond Rozen, and he's well known in Victoria, and as you've seen, he's written numerous trial exam papers for methods in specialist mathematics and is a co-author of the MathQuest series. And like Peter, he presents at state conferences and at T-Cube International using the TInspire. So welcome, gentlemen, and over to you, Raymond, to start the evening.
Okay, so everybody hear me? I'm on. Welcome to today's webinar on complex numbers. The first half of this, I'll be presenting some sort of basic theory up on complex numbers and getting into some more advanced features. So let's get started. First example we want to look at is to say find the square root of -9, and the second example here is to solve the equation x squared plus 9 equals 0. Now these are totally different questions. A lot of people think they're the same question.
Sorry to interrupt, Raymond, I can't see your screen. Have you shared your screen?
I haven't shared my screen.
So if you click on the Quick Start tab and share your screen.
Yeah. Sorry.
There you go. Thought it might have been me up here in Queensland.
All right.
There we are. There we are. You've got your screen now, Raymond.
Okay. So, sorry, my name's Raymond Rozen. My email is there, and today we're doing a bit of an introduction to complex numbers. So let's look at the first example, finding the square root of -9 and solving the equation x squared plus 9 equals 0. Now, if we want to find the square root of -9 on a calculator, let's just hit the control square root button and use minus and hit 9 and then press enter. Now I know something's going to go wrong here. It says the result is a non-real number. Now, this is done on purpose. The reason this has happened is because we're in the wrong mode or the wrong settings. So if we press the on button and then hit the settings command, we'll go to the document settings here. And one of the document settings that we're looking at here is the real or complex mode. When we work in complex numbers, real mode will not suffice. We have to be in rectangular mode. So let's change the real or complex mode to rectangular and go to OK. Go back to our current document, and rather than typing it in again, if I just go up arrow and then press enter for the square root of -9, this time we get 3i as the result. Note that it is very important that there is only one answer to this question, -3i. I is the complex number. If we want to get the complex number, one way of getting it is from this pi button on the side, and we'll hit I, and the definition of I is that I squared is equal to -1. All right, so now the other question that we wanted to look at then was solving that quadratic x squared plus 9 equals 0. Let me just type in x squared plus 9 equals 0. And if we try the algebra command, solve, we want to solve an equation, x squared plus 9 equals 0 for x. Once again, the calculator will come up with false. The reason being is that there are no real solutions for this. So rather than going to the solve command via the normal algebra menu, what we want to do this time is go to the complex menu. So the complex menu is solve. Now the only difference here is that it puts a little c in front. So it's c-solve. So c-solve, x squared plus 9 equals 0 for x, and that will give me the two solutions, x equals plus or minus 3. So notice that this one has two solutions and is a different question than the other one, which only had one solution for the square root of -9. Okay, so let's look at complex numbers in general here. A complex number is composed of two parts. It's x plus yi. It's one single number which has got a real part denoted by x, or rex, rez, and imaginary part. Also associated with a complex number is what's called the conjugate, which is denoted by z bar, which is x minus iy. All right, let's just have a look at another example of that, where we actually try to solve a more general equation of a quadratic. And this time we'll try to solve it with z squared plus 4z plus 13 equals 0. Once again, if you know the menus, then you can just type them in. So c-solve, z squared plus 4 times z plus 13 equals 0, solve for z. So notice this time we get two complex numbers, z equals -2 plus 3i or -2 minus 3i. Now, we said a minute ago that those two complex numbers are related. They are in fact the conjugate. So let me just say, for example, store. So if I say z is assigned equal to -2 plus 3 times the complex number I. Now, you have to make sure that whenever your students are using complex numbers, they don't type the letter I. They must use the I from this template here. So given that there's one single number, now a lot of people are not sort of happy that a complex number's got a plus sign in it, but it still is one single number composed of two parts, a real part and an imaginary part. Think of, say, the number 3.4. That's really 3 plus 0.4, which has got an integer part and a fractional part. If on this one complex number, we go to this menu and complex number tools down the bottom, if we want to extract, just do that one again, menu, a number, complex number tools. There's the complex conjugate. Now we're going to have a look at a lot of these menus in this command here. Let's just try the first one, real part. So if I type in the real part of the value of z, it just returns -2 as the real part. Obviously, you wouldn't need a calculator to do that one, but let's just look at all these tools. Some of these are more useful in other aspects as well, which we'll see perhaps later on. So the imaginary part is 2, and let's just try one of the other operations there as well. Another operation there was number 1, complex conjugate. So conj of z. So conj of z, notice it's just the change in the sign of the imaginary part. And if we are in fact to multiply the conjugate times the original number, then we get a real number. So the conjugate is useful in that respect in operations dealing with complex numbers. All right, well, let's just have a look. Now, we want to visualize the roots of a quadratic equation. We know that if we've got a quadratic equation, the roots are where the complex number, where the quadratic crosses the x-axis. But where are the roots if they're complex conjugates? Well, it's a very interesting sort of question I think I've raised here. Let's just have a look at what's happening here of this quadratic equation. When we've got a quadratic equation, the two red dots are indicating two real roots. And this is just a quadratic equation illustrated with sliders for A, B, and C. We won't change the values of A and C, but we note that this graph crosses the x-axis twice. As I change the value of B, we're seeing that the two roots are getting closer to one another. The discriminant before was positive, now the discriminant is 0 when we've got one real root. if I change this quadratic even further to get the one that we had before, we notice that the roots have now gone into a sort of a two-dimensional situation. And this is sort of how we can plot complex numbers, not on the real axes x and y, but on an imaginary axis called an Argand plane. So here, also very interesting to note is that the x values, or that the real parts of the complex number, the real values of the complex two values, is also equal to the x value of the turning point. And there is a relationship between the y values of the imaginary parts of the complex number and the turning point of the y value of the quadratic as well. So I'll let you investigate that one at a later stage as well. Okay, so basically here we can say a general situation. If I've got a quadratic equation, az squared plus bz plus c, a, b and c are real numbers, and the nature of the roots depends upon the discriminant, b squared minus 4ac. When the discriminant is positive, we know that there are two real distinct roots. When the discriminant is 0, there is always one real root. And if the discriminant is negative, then not only do we get complex roots, but in fact they occur in complex conjugate pairs. So we know what the conjugate of the complex number now represents as far as that situation. All right, now when we look at complex numbers as a new quantity, just like when we study matrices or we study vectors, we have to learn the operations associated with complex numbers. And this form of a complex number is called the rectangular form. So if we've got two complex numbers, we want to add or subtract them, the rules are we add or subtract the imaginary parts separately. If we want to do multiplication of two complex numbers, then we just basically proceed as we would in normal algebra and replace the I squared by -1 when it appears. To divide two complex numbers, what we're going to do is we're going to multiply the denominator and the numerator by the conjugate of the denominator. Now, this process is basically the same as what you would have done in year 11, such as rationalizing the denominator by multiplying both sides by the conjugate of the denominator as the third. So instead of rationalizing the denominator, this is called realizing the denominator here. Same sort of basic procedure. All right, now, as I said before, we've got two complex numbers. If I've got two complex numbers, say Z1 and Z2, although these complex numbers are actually just the points, so don't draw these lines if you're asked to draw a complex number. The complex number is just the point. But notice that the x1 and the x values, when I add them, give me the solution of -1. So effectively, although complex numbers are a different thing to vectors, they basically add and subtract in the same sort of way. So really, complex number questions or vector questions are similar in that respect. The vectors have two components, an I and a j component. A complex number has a real component and an imaginary component. But effectively, they're adding the same way, and a lot of the algebra performing on them is the same as well. So we can move a number of these points. So these complex numbers and vectors, another name for that is basically an isomorphic situation to show you that they have the same sort of structure. All right, so let's have a look at a simple example now where we've got two complex numbers, u and v, and we want to now find some other complex numbers associated with them. So again, on a calculator page, let's just store some of these complex numbers. Now, we all know that we can store real values, we can store functions on a calculator. One of the things I'm going to do now is store u as assigned equal to. So notice I've got assigned equal to, and this will be the complex number 2 minus 5 times I. Once again, make sure you use the complex number I.
Instead of typing error.
Minus 5I. Okay, now that's one way of storing. Another way of storing is to actually type in the number minus 3 plus, this time I'll type in 2i. Now this time I'm going to use the store command. and we're going to store that to the complex number v. Effectively, those two operations of assigning equal to and storing are effectively the same. We could have also used the define command like we use for functions. But just an interesting way of storing. Having defined those two complex numbers, we can perform all the algebra and get all the results that we want. Again, notice that when I type them in, they become bold because they're predefined variables. So if we want u to the power of -1, the calculator will automatically rationalize that or realize that. And if we want to multiply the complex number u times the complex number v, the calculator has already calculated that for us. And also we can do a division as well, u divided by v. Now, these are results that are obviously coming up straight away. Obviously, for an exam 1 type situation, questions like this you should be able to do by hand. But in an exam 2 type situation, you probably want to use your calculator to perform results such as these. In fact, we could even do some general results of these situations. If in general we wanted to say Z1 is assigned equal to A plus B times I, and Z2 is assigned equal to C plus D times I, then we can have some general results for Z1 plus Z2. Notice that the real parts, A and C, have been added, and the imaginary parts, B and D, have been added. We can multiply them as well, Z1 times Z2. We've got a general formula there, or for Z1 divided by Z2 as well. Of course, these are just general sort of results. Yes?
The question is, some people suggested that possibly they like using the template, the catalogue template, the keypad to the left, there's the templates, the equations, they like using control assigned there, don't they?
Yes, that's the same thing. I just typed it in. So here you can go control equals or control template. That uses the assign command as a storing facility as well.
Yeah, thank you for doing that.
Lots of ways of effectively creating the same situation. All right, now another little interesting situation is to sort of visualize a complex number. Now we can't really plot a complex number on the normal Argand diagram, on a normal XY Cartesian coordinate system. So what we're going to do is we're going to pretend that the XY Cartesian system is the Argand diagram where we plot the complex number. So for example, if I've got a complex number u equals 2 plus 3i, where is the complex number the conjugate, and where is I times u? So we want to comment on their relative positions in relationship to the original complex number u. So let's just work out, well, I've assigned u to be 2 plus 3i. The conjugate we know is 2 minus 3i. I times u is going to be 2i plus 3i squared, which is going to be minus 3 plus 2i. So where is those 3 points? Let me just plot those 3 points for you. This has already been prepared. So there's the complex number u, there's the complex number u bar, and there's the complex number iu. So what is the relationship here for u to u bar and u to iu? From that little picture, we can't really see it that clearly, but if I go to the next slide, you'll see what's exactly happening here. This time we can see that the angle here and this angle down here are the same. And the angle between u and iu is in fact 90 degrees. Notice the position here, the 2 and the 3, the coordinates here are minus 3 and 2. So what's the relationship? The u has been reflected in the real axis or the x-axis, and the iu has been rotated 90 degrees anti-clockwise. And this happens for any complex number that we see. The u is always the reflection, and iu is always, that angle is always maintained at degrees. So the conjugate is the reflection of the complex number in the real axis, and multiplying by I is a rotation of 90 degrees anti-clockwise of a complex number. this is an interpretation of complex numbers. We know how to count. We can say there's 3 cars or 4 cars, but what is the complex number I? Well, it's a rotation 90 degrees anti-clockwise. This does have sort of applications in electronics where we have currents and things out of phase by 90 degrees, and we can have complex currents and things as well. So we don't deal with those sort of things in specialist math, but I think it is very interesting to visualize those complex numbers in that respect. All right, let's have a look at some other little questions here. Cubic, we've solved quadratic equations. Let's have a look at a cubic equation. Now, in solving a cubic equation, if we look at the graph of that, we think, well, it could cross the real axis 3 times, which is going to give me the zeros of that quadratic, cubic. Another possibility is that there is one real root and it doesn't cross anywhere else, so therefore we get complex conjugate roots. Or another possibility is that the graph touches the x-axis at one point, and that'll be a turning point, and also then 2 other roots. So although it's a cubic, we're getting 3 roots, there always must be one real root. And that little statement there and the statement about the quadratic having complex conjugate roots are dealt with later on, and Peter may talk about conjugate root theorem or the fundamental theorem of algebra, which are generalized statements of that. Often in specialist maths, they've also had questions on solving cubic equations, where in fact not only do we want to solve a cubic equation, but in fact we want to find the sum of the roots of a cubic equation. So let me just type in that cubic equation, for example, which was what, z cubed minus 5 times z squared plus 11 times z minus 7. Okay, now one thing I didn't show you before was the factor command. So if we go menu, algebra, and factor. Now if we try to factor that expression, remember this is not going to work. It only gives me one real factor. It didn't factorize the quadratic factor. If I want to factorize it into linear factors, then rather than using the algebra command, I'd have to use it from the complex number tools here. Complex number here is factor, but effectively that's just going to give me C factor. So rather than doing that, I'll show you a nice little neat way of doing it. Just grab that one, scroll to the very front, and just put a C in front of it, and it'll give me C factor. C factor didn't work. Sometimes it requires a comma Z to tell it the variable name. So this time it's factorized it into linear factors. One other command we didn't look at before, in the algebra command for solving complex, there's solve and factor, and there's zeros. So we know what solve does, or C solve or C factor. Let's look at zeros. So if I go C zeros, now when I solve an equation, we have to solve that equation equal to 0. If I go C zeros, we don't have that equation equal to 0, we just have that equation. So we just go comma Z here. Now this returns the 3 roots in a list, okay? So those lists are the 3 roots there. Now, the question was to find the sum of the 3 roots. We want to find the sum of the 2 complex conjugates and the other one. We can just type in sum of that list, and it'll return the answer 5. So it's really exactly the same as going C solve that equation. If we go C solve, we have to go equal 0, comma Z. So there we've got the 3 roots, and we've added them up in one hit to produce the sum of the roots. So that little question, if we look at that one before, that sort of question has been like a multiple choice question in specialist maths for solving an equation. Okay. Solving 4th degrees, well, they're done exactly the same way. If I wanted to solve a 4th degree, I could do exactly the same as what I've done on a calculator page for the last little question. We can type in these things: factor, z squared, z to the 4th, plus 3 times z squared, minus 28. Again, it gives me the 2 linear factors, but it won't do the quadratic factor. unless I do C factor. We could get the C factor, but I find it easier to sort of type things. Still didn't work. So what happens? We have to put in the comma Z. And again, we can go C solve. Typing these things in, I think once you know them, is often easier than grabbing them from the menus. But this time I need to type in the equation again. Z to the 4th plus 3 times Z squared minus 28. But now we have to type that in equals 0, comma Z. So C solve is the thing that we have to use here. All right, it's given to me in, didn't type it in correctly, Z to the 4th. Okay, so it gives me again 1 pair of complex conjugate roots and 2 real roots as well. All right, I think I'm probably gone a bit over time now. Maybe we can leave the polar and rectangular form of a complex number for another session, or maybe Peter might like to do that. So I'll go on for my share of the time. I'll hope you enjoyed that bit of introduction to complex numbers. There's a lot more in complex numbers that we can do, rectangular and polar form, as well as subsets and solving general polynomials and things like that. So welcome to Peter. Was there any questions regarding my session there?
No, there are no further questions there. It was fabulous what you just said there, reminding people about C solve, let it equal 0, and then the C factor and so forth. It's fabulous to remind people of those little things.
Okay, thank you.
So we can see Peter's screen on the webinar, and you're right to go, Peter.
Yes, thank you, Rodney. Thank you, Raymond. So a lot of this work is Raymond's work, so it would be a very good idea that I laud him for this. I'm just a bit of a hanging by his coattails here for this particular session. So one part of the specialist maths course is to find and graph the Cartesian equation of a subset of the complex plane. This part of the syllabus has undertaken a recent revision for 2016 onwards, in that students are only asked to consider circles, lines and rays. So you won't have any questions relating to inequalities, working out areas, etc., etc. And what I've noticed over the years in specialist maths exam questions is that the TInspire CAS is actually really useful for answering such questions like, let's consider, a subset of the complex plane. It might be a circle. Another subset of the complex plane might be a ray, and you might want to find the intersection of the circle and the ray. And what happens is that the CAS actually scaffolds the students nicely and performs sometimes some quite difficult algebra. So it's well worthwhile having a look at this from the perspective of exam questions just to start off with. I suppose another note that Raymond and I need to say is that we're not affiliated with the VCEE, so our comments are independent of that particular statutory authority. But here's a pretty simple example that Raymond has set up. He's saying find the Cartesian equation of S, find the Cartesian equation of R, and then find the coordinates of the intersection of S and R. Students hopefully should see that S is going to be a circle and R is going to be a ray. Also note that that's the principal argument, capital A. So if we have a look at the next page, what Raymond has set up here is to give you the beginnings to how powerful the calculator application, and indeed the notes application if you were to work in the notes application, how powerful the simplification functionality of the device actually is. So what Raymond's done here in the first calculator line is he's defined Z to be X plus YI, and as Raymond correctly pointed out, a big boo-boo that can be made is to use letter I rather than complex number I. Then in this second calculator line, what he's typed in there, he hasn't gone and found the absolute value bars. He's typed in or found the absolute value commands, which is ABS. So he's typed in ABS open bracket Z minus 2 plus I close bracket equals 5 and pressed enter. And what he's received is an expression in terms of x and y, and that's come about because he's defined z to be x plus yi. And moving from that second line there, so you've got what looks the potential for a completing the square type task underneath that square root sign on the left-hand side, the right-hand side equaling 5. Then come down to the third line here and say, well, I'll just square both sides. And so you end up with that expression there equaling 25. And a really interesting feature of the algebra set of commands is the complete the square command. And the nice thing about the complete the square command is you can do it in terms of x and y. So you can take an expanded left-hand side, and then by completing the square, you can collect the terms up, you can write them as perfect squares, and you can end up with the more familiar form of a circle. So to get the complete the square command, it's just a matter of pressing menu, and then number 3 for algebra, and then it's number 5 for complete the square. Also note that to complete the syntax there, to complete the square both on variable x and variable y, we've used a comma after the 25 and then curly brackets and parentheses surrounding x comma y. And when you press enter, you get the Cartesian form of the circle, x minus 2 all squared plus y plus 1 all squared equals 25. So we've got a circle with centre 2, -1 and a radius of 5, which students should be able to pick up from this form up here, but it's nice to be able for students to see the equivalence between that form of the circle in the complex plane and then its corresponding Cartesian equation. So the curly brackets are just obtained by pressing Control and then normal opening brackets. So that's an excellent page that Raymond's set up, and it gives you a bit of a teaser for answering these types of questions. So if we move to page 16.2, you can tell that Raymond has made this because there is actually a 16. If I was making this, it would probably only be about 1.3 and would have run out of ideas. But Raymond's knowledge of specialist maths is outstanding, and we're seeing this here. So if we go to page 16.2, now notice that back on the previous page, z is defined as x plus yi, back up here, x plus yi. And then top of page 16.2, which again is a calculator page, what Raymond's done is he's now typed in, using TInspire, what would be a representation for that ray that was defined back here. So R being the set of z values such that the principal argument of z minus 2 equals -pi/4. We'll see graphical representations of this in a moment, and in fact the way I'm doing this, it might be better to see the graphical representation first before doing the prerequisite algebra, but I'm just doing it in the page order here. So really what we've got is, if you think about this, z is x plus yi, so you end up with the arg of x plus yi minus 2 equals -pi/4. And so in moving from that to the Cartesian form, you can therefore say that y on x minus 2 is tan of -pi/4, and tan of -pi/4 is -1. So by multiplying both sides by x minus 2, you end up with y equals 2 minus x. And so what you'll also glean is that x is greater than 2 and y is less than 0. And what is really interesting is if you just type this in without that restriction that y is less than 0, what happens is you get a puzzling output. So this can sometimes occur when using CAS, that if you don't pay close attention to restrictions or domain constraints, or in this case like a range constraint, you may end up with a problematic output that could throw the students, which is interesting. what happens here is we've got the signum function. So to prevent such situations from occurring when using TInspire CAS and other CAS for that matter, it's prudent to always, when you're solving equations and you know that there is a restriction that needs to be applied, then apply that restriction. And so what Raymond's done here is he said, well, okay, let's take this puzzling output, or we could also have done this with the original sensible output. Let's solve the equation for y, given y is less than 0, and so therefore we get the Cartesian form for the ray, which is y equals negative times x minus 2, and the condition is that x is greater than 2. It's just written in a slightly different form here. Just going back to this line here, if you wanted to get the command angle, it's a matter of pressing menu, then 2 for number, then 9 for complex number tools, and then you've got polar angle there, for example.
Peter,
so
quick question.
Yep.
Where do you, on the calculator, get the given command? So given that y is less than or equal to 0, one of the questions has been asked.
So the given command, for example, if you press Control equals, and what will come up, you've got that little box with those 6 symbols. And if you want to save 7.3 milliseconds in the exam, rather than arrowing to the right and arrowing down, if you just arrow to the left, just takes you straight there. That's the given symbol.
Thank you for that.
Thank you, Rodney. So that's how you do it on the handheld keypad, and then on the computer, Shift and then one of the slashes, you'll be able to get it as well if you're using the computer. So we end up now down here, and this is some good work here from Raymond. He's also showing us that we can actually graph these 3 regions. Very sneakily, he's defined f1 of x to be the zeros. Now, the zeros command, whatever you type in here, it's assumed to be equal to 0. So that's why you've got that subtract 5 there. So anything that you type within zeros, it's assumed to be 0. So basically, 5's been subtracted from both sides and then solved for y. Then we've got the Cartesian form defined here in f2 of x. And then interestingly, in f3 of x, we've got the angle of, or the principal argument of z minus 2 plus pi on 4. What I neglected to say just a minute or so ago is that when considering rays, in this instance, x is greater than 2. So on the real axis, that point 20 must be represented by an open circle. It's because you end up with an arctan where you've got a denominator that's undefined. So if we go to this next page, what Raymond is illustrating here is, let's say we want to find the point of intersection of this circle and this ray algebraically. He's showing from the perspective of, well, here are the 2 Cartesian forms. Then you can actually do this a little bit more prudently by having the right-hand side, I think, expressed in terms of angle z minus 2. I haven't actually tried it, but I think it would work. So anyway, here's the circle, and there's the ray, and we're solving it for x and y, and we're saying, all right, we want to put in the constraint that x is greater than 2, and so you get x equals 6 and y equals -4. So in other words, 6 minus 4i is the point of intersection on the complex plane of that circle and of that ray. And this one down here, I presume that Raymond has very cleverly put this line in without the domain constraint, And then if you know your geometry reasonably well, you would expect, if you were allowed to extend the ray up through the first quadrant, crossing the positive part of the imaginary axis, you would get another solution at -1 plus 3i, but of course that's not allowed because of the definition of the ray, or it's a half line, might be another sort of colloquial term for it. So this also is an excellent illustration of the need to insert a domain constraint where a domain constraint or a restriction exists. There are occasions where such restrictions are inputted and it doesn't actually help. I can't think of one off the top of my head, but I have experienced it before in the past. But in these types of questions, as I said, whenever there's a domain constraint, pop it in. And then if we go to this graphs page here, note that you could put an open circle there to suggest that it's undefined at 2, 0. And then if we have a look at what Raymond's very clever work here, he had f1 of x, f2 of x, and f3 of x defined on the previous page. And this is what it looks like in the respective entry lines. And you get that point of intersection there at 6, -4, which corresponds to 6 minus 4i. So the point that I want to finish up with in terms of subsets of the complex plane is that the overwhelming majority of the time, the CAS is actually, the symbolic part of the CAS, or the symbolic part of the TInspire CAS, should be the student's friend. So if the student goes back and has a look at past exam questions of this ilk and tries them out using the CAS, I'm hoping that they'll find that they'll get their answers quite readily. They will have their algebra scaffolded because, you know, that the CAS is essentially unerring. If you put in the right input, you should get the right answer coming out. One weird thing that the students may need to consider is sometimes in these questions there's about 9 or 10 lines of work required, you know, line by line of implicit reasoning. What happens when you do a question like this in this environment, as Raymond has shown here, is basically we've just got, you know, a one-line input and then an answer. So what happens is that the solutions are far more compressed than what they normally would be for a student doing this by hand. So I think it's well worthwhile as a teacher to discuss the different nature of the solution that you would obtain using a CAS compared to by hand. It's more compact, the reasoning sort of more upfront, and it's just a matter of just communicating to examiners with correct mathematical notation, conventions and syntax what they're doing, and then being able to interpret their answer correctly. So well done, Raymond, for preparing that. We might go on and quickly now in the last 10 minutes have a look at a little bit more of a visual illustration, power of the CAS to help us visualize important theorems that students need to know and apply in complex numbers. The first one here, this is a lovely demonstration that Raymond has constructed, which looks at the nth roots of unity, or in other words, solutions to the equation z to the power of n equals 1. And this has been set up on a notes page with some math boxes. And so what we've got here is we've got a math box for n equals 3. I'm just pressing tab here. And then what Raymond's done is he's defined, and because we're going to end up graphing in terms of our independent variable is going to be x, unfortunately, well, it'd be great if we had it all in terms of z, but we just need to mention to the students that, you know, that we're using x, so make sure they don't get confused between x and z. So, and also Raymond has shown you the assign command. So I think that my preference would be for students to use the assign command. If I was teaching a class of strugglers, I'd be probably more inclined to use the define command, and the reason being is that sometimes I think the strugglers can just forget that it's colon equals, and they'll just put equals rather than the colon equals, and that can cause problems. So I think it's a judgment call. Before anybody asks, there's no difference between define and assign. I just find it easier to use assign. It's quicker and there's less real estate taken up on the screen. And then if we come down here, we've got a list of the roots. So these math boxes, the way that the attributes have been set up here by Raymond is that we're showing the output only and we're hiding the input because the students don't need to see the input. They are seeing the input when I click in the math box. So Raymond's assigned Z1 to be the complex poly roots of f of x of x. So therefore you get your list of roots there. And then what we can do is we can assign XL to be the real parts of ZL. So they're the real parts, -1/2, and 1. And the same with the imaginary parts. Okay, so what we're going to do now is if we have a look at the next page, you can set this up because what Raymond's done is we have lists here. We've got XL and YL, or X1 and Y1, they could be. My eyesight is going on me. So what's happened here, now this is an interesting point actually for statistics and probability for methods and specialists in Unit 4. One of the applications of TInspire is data and statistics, and this is a data and statistics page, and this is showing a scatter plot of X1 and Y1. Now, at your school, the further maths teacher or teachers will be expert in this environment. Because of syllabus changes for the start of 2016, which includes a reasonable slab of statistics and probability, the math methods teacher and the specialist maths teacher also need to have a very good idea how the data and statistics application works. So if I was a methods teacher or a specialist teacher, I'd be leaning on the further teacher throughout the lead up to the teaching of statistics and probability, and also Texas Instruments will also do some webinars on some further maths, and I think that it's well worthwhile methods and specialist teachers actually having a look at the further webinars just to see how this environment works. What we can also do is we can show these roots on a more familiar environment, which this is a graphs page, and we're using the scatter plot here. So what we've got is we've got a clicker or a slider, and so what we can do is we can change the value of n, and it will give us the roots of unity. So this is very nice so far. We've got n equals 3. We've got 3 roots, lies on a circle, which we can choose to either show or not show. So you can click on that to hide it or bring it up again. And we've also got this angular spacing. So for example, at the moment, the angular spacing or the angular separation between the roots is 120 degrees. And so if we even go down to n equals 2, well, they both lie on the real axis, and the angular separation is 180 degrees. We go up to n equals 3. We've got 3 roots. We've got 1 on the real axis. We've got 2 not on the real axis, but they look like they're complex conjugates of each other using that geometric property that Raymond espoused in his 25 minutes. So then what you can do, this becomes a little bit like the old predict, observe, explain type teaching approach that the physics method lecturers used to teach in the 70s and 80s. So what do we predict to see when n equals 4? Well, hopefully we see 4 dots representing 4 solutions. Righto, so the angular spacing is 90 degrees. So it looks as though there's a functional dependence upon n, and as n is increasing, the angular spacing is decreasing. So that's quite interesting. Note here that we've got 2 roots there on the real axis and 2 purely imaginary, aren't they? So n equals 5, 72 degrees. What you can do is you can really herb it up and you can do an animation. Right, so there we go, it's animating, which is very nice. So I think we've only gone up to 20, otherwise we didn't want to overcook it. So there's lots of things we can talk about here. We can start to talk about coming up with generalizations for the angular spacing. We can talk about how many roots would we have on the real axis for a particular, say, even value of n. What should the situation be for a particular odd value of n? And rather than doing this in a static way, we can actually give students an opportunity to make some predictions and to see what's happening when we change the value of n. It's not a good idea to have this notes page and the graphs page that I just showed you. It's not a good idea to have it as a split page because it just becomes too busy. Just in the background, my dog is about to bark because there is a dog being walked outside as we speak. So that's pretty much the fundamental, that's pretty much the nth roots of unity. I think Chappie might be hungry as well. What we can also do with Navigator is we can ask questions, you know, like along the lines of when n is odd, there is always one root of the equation z to the n equals 1 located on the real axis of the complex plane. Is that true or false? So we can also do this quick polling of the students. It's this immediacy informative assessment which is so fantastic, and it's a really great card that Inspire brings to the table. So just in the final, there's a few more questions there. So in summary, the solutions of z to the n equals 1 lie on a circle with centre, the origin, and radius 1. And what we can end up doing is we can determine that the solutions are equally spaced around the circle at intervals of 2 pi on n. We felt it was a good idea to have the angular spacing in degrees. It's just easier to see the pattern, you know, 120 degrees, 90 degrees, 72 degrees, 60 degrees, rather than the decimal form for radians. You could also plot those values on a scatter plot and get a curve of best fit. That would be quite interesting as well. So just finally, we can also show you the roots of an nth degree polynomial with real coefficients. And so what we've got here is we've got, we're using the random polynomial command. And there's a very good reason that Raymond and I will share with you one day, is that you don't want to show the explicit form for f1 of x. Just show the box here with rand poly in it. And this is a split page. The bottom sort of half is a notes page. So again, we've got the roots, we've got the real parts, and we've got the imaginary parts. And they are plotted on the graphs page using a scatter plot feature. And so in this circumstance, for n equals 3 real coefficients, we have one real root and a pair of complex roots, and they appear to be complex conjugates of each other. We also have a page where we blow this up a little bit, and then what we can start to do with students is we can say, well, all right, let's start changing the value of n. So this is widening the nth roots of unity demonstration to look at families of polynomials. So this at the moment is cubics. So we've got 3 solutions. So we're not counting solutions, we're not counting multiplicities, if you know what I mean. So if we go to n equals 4, that's an interesting one. So what we've got here is we've got 2 pairs of complex conjugates. Go to n equals 5. So this is odd again. 1 real root and 2 pairs of complex conjugates. And you can say to the students, well, what do you expect to see for n equals 6, n equals 7, for example? So again, what seems to be happening is that we're guaranteed a real root, when n is odd. So we want students to list all these various properties down, I think, as they go through the visualization process, because I think it leads to a greater appreciation of what's going on and a better conceptualization and conceptual understanding of what's going on. You could also animate this as well. So we can bring this back to n equals 3, for example, n equals 4. So that's updating the roots and the real parts there for you. And as I said, you can blow it up. I can really blow it up by what's going to happen when we animate. Right, so there's 5, 6, 7. Sometimes you might see a fish. Other times you might see something that looks closer to an elephant. Sometimes, because of the window, you mightn't see all the roots. Just occasionally one will end up being outside. But generally, from -4 to 4, we seem to be able to capture them. All right, so if we stop the animation there, so that's a 19th degree polynomial. So you've got, you can count up all the complex conjugate pairs, how many are real, etc., etc. Those scatter plot points are being housed inside that list and spreadsheet page there. If I just click on tab and open up the graph entry edit line and show you the scatter plot, see, that's what's going on. So the lists are called X real and Y imag, and and then they're being housed in the list and spreadsheet page, and then they're also being displayed here on the graphs page. So that's by changing the graph entry edit. Just pressing tab through here. So if you press menu, graph entry edit, you've got function, but you've also got this scatter plot feature. I think that methods and specialist teachers need to understand how to use the scatter plot functionality of the graphs feature. And final remark coming up, we've got a few more nice questions as well. If p of z is an nth degree polynomial for odd n, there's always one real root of the equation p of z equals 0. Is that true or false? So what we can do is we can poll the students and see what their understanding of the situation is. And some of these questions are really good, challenging questions that have been devised by Raymond, who is an excellent question setter. So I think I think I like this one here on page 5.9 as well. If p of z is a polynomial in z of degree 5 with real coefficients, then which of the following possibilities is correct? And then, of course, we can talk about formalising the fundamental theorem of algebra and also formalising the conjugate root theorem, which is really important. So on that note, I'll pass it over to Rodney. Rodney?
Thank you, Peter. You're very correct there. The visual aspect is very powerful for students, isn't it? So you can see the diagram, what's happening, and then it just ties in what they're doing algebraically. So summing up like we normally do, I like to show you the Texas Instruments Australia website. So if you're not sure, the website's education.ti.com / I generally just type in Australia, and then we have the TI Australia website. And if you're looking for the previous recordings, in the middle of the page here, we've got the webinars. And we select that, and here we are. So tonight, we've just had this one here, the Specialist Mathematics Unit 3 Complex Numbers. Tomorrow night, we've got the Mathematical Methods with Frank and Bojana. And then, as we've got a few more coming up, please register and have your name in the mix ready for the webinars. And if you've got time, you could think, okay, I want to see previous recorded webinars. So we click on the On Demand tab, and there we have the previous webinars. So last week we had John and Jim presenting on the TI-84 CE and the TI-84 Plus, and they have the webinars. You can play online straight away, couldn't download it and save the external hard drive, and then you've also got the files here as well. So, and as you see on the right-hand side of my screen, there's many, many, many webinars that have been recorded with various trainers, excellent trainers around Australia and hosts. So it is all there for you to have a look and take your time with it. So at the conclusion of this webinar, please take the time to complete the survey and help TI Australia improve on their excellent webinar series. And obviously in the next day or two, you'll get your follow-up email, which will contain the certificate link as well. And take care, and we look forward to your participation in future webinars. Good evening. So thank you to Peter and Raymond.
Thank you. Bye.